my name is Sebastian Mengwall, a senior at Darien High School, and I am presenting my research, Cloud Identification in Mars Daily Global Maps with Deep Learning. I have designed a deep learning framework that identifies Martian clouds and can replace the existing manual and semi-automatic techniques. It identifies clouds at 97% accuracy and at high resolution and high speeds. So clouds play a large role in the atmosphere of Mars, and understanding them will aid us in developing better climate models. This can also be helpful for us for future Mars missions by rovers or even humans, because we can plan ideal mission locations and also warn for incoming storms. The two major clouds that we see on Mars are water ice clouds and carbon dioxide ice clouds. In addition, there are also dust storms that interact with these water ice and carbon dioxide ice clouds. And the two major locations that we can see clouds are in the tropical cloud belt, which is at the tropical latitudes, and also polar hoods, which are cloud locations over the polar ice caps. In the summer months, these are very active. On the left side, we can see a nice global satellite image where clouds are quite active on Mars. And we also see, this is an image of the Curiosity rover looking up at the sky, seeing some nice wispy clouds on Mars. The products we will be using to get information about Mars are the Mars Daily Global Maps. These are composite images created by Mars Color Imager, an instrument on the Mars Reconnaissance Orbiter, and that was released in around 2006. And this collects information daily on Mars at 0.1 degree spatial resolution. And this gives us great temporal and spatial coverage because we already have over 6 Martian years worth of data, and this is still active in use. And the potential implications of this study is that we can better understand Martian climatology. We can also test and train global climate models based on what our model sees in the clouds, and we can actually potentially assimilate machine learning and deep learning models into these climate models. And we can also use, we would like to see whether machine learning and deep learning techniques can be used in planetary science studies. This is one of the earlier representations, and it's new to the field. I believe that convolutional neural networks will be successful in extracting cloud masks from Mars Daily Global Maps, dramatically increasing data coverage and minimizing human input. These cloud masks give scientists a range of data on where clouds are, pixel for pixel, daily on Mars. So they would be able to see where clouds are and where clouds are not. This is a brief overview of the model that I trained and made. This is a modified UNet model, which is a convolutional neural network, which is quite popular for segmenting visual imagery. And the major breakdown is that we have a decoder path, which comes down here, where we begin with a 668 by 668 image, and we compress it down by doing some convolutions down to something which is around 38 by 38 pixels. And this gives us some information on the general features where clouds are most likely to be located in regions. And then we bring this back up through a decoder path and connect it with earlier information so we can try to pinpoint exactly where clouds are on Mars and give us the most accurate cloud mask for the given image. I've also made some modifications to this UNet, including batch normalization and a ReLU activation function, which will help with performance and also training speed. To complement this UNet, I have also created multiple pre- and post-processing techniques to address certain properties of the Mars Daily Global Map images, and also to avoid misclassification of ice that exists at the polar ice caps. So to avoid misclassification, I segment off the lower and upper latitudes based on these equations, which take account for solar longitude, which is simply a measure of time since the spring equinox. And this is uniform throughout Mars and commonly used. I have also created a smooth tiling program that takes an inputted at Mars Daily Global Map and subdivides it into slightly over, it varies based on the image size, but over 50 smaller segments, and then stitches the predictions together into a full 3600 by 1801 map. And here's a quick breakdown of the pre and post-processing pipeline that I use and have created. In A, we can see a standard Mars Daily Global Map image. In B, I have segmented off the northern and southern latitudes to protect from misclassifying these carbon dioxide ice clouds and other ice. And these are just representations of the subdivisions that I created of this Mars Daily Global Map. And the predictions of these subdivisions are then weighted so that the center of these predictions are weighted more than the edges because they have more information around them. So each pixel that has the greatest prediction is then included in this final Mars Daily Global Map, which reports negative 999 for an invalid image, 0 for no cloud, and 1 for a cloud. And this is a quick observations of my training. I trained multiple versions of my model, which are shown in the leftmost column over here. And I also monitored 3 main statistics: loss, accuracy, and the Jacquard index, also commonly known as intersection over union. I decided to go with my 32-width V2 model, which has the greatest accuracy and Jacquard index, and it also performs the best in real-world scenarios. In A, here's another example of a Mars Daily Global Map image with the light blue dashed lines representing the northern and southern extents that I took out, and also the lime green represents an overlay of the cloud mask that I created. And then the red square represents a subdivision, the size of a subdivision that I would be taking. And then B through E, which we'll revisit later, are just focusing on this specific subdivision. And through these subdivisions, we can see the high resolution and the cloud mask detail that this model offers us. We can see fine features, and we can see nice curves and striations throughout the clouds, as we can see in the upper right corner of A. And also, these cloud masks, because of their high precision, can be used for local and precise global analyses. And its comparison to the target, which is our training data that we looked at, which was created by Helen Wong and Gonzalo Gonzalez-Abad back in July of earlier last year, we have noticed that my model has finer features and is able to get rounder edges and more naturally represent the clouds on Mars. And we also see slightly greater cloud extents. And as we can see, this is C, which is what Wong and Gonzalez-Abad made. This is my model's interpretation of the mask for the same image. And when we overlay them, we can see in some areas slightly larger extents, but though we believe these to be actually accurate and not exaggerated. And because of that, we are able to compute these masks so quickly and over a wide temporal range, we can do lots of interesting analyses with these cloud masks, as we're going to show in the next few slides. So here is a brief look at Martian cloud frequency evolution over the tropical cloud belt, which is in the middle latitudes and lower latitudes. We can see that clouds, what this is in images is of a composite of over 3,300 cloud masks that the model has been able to create very quickly. And we are able to average them together to get a mean cloud mask cover, a cloud mask frequency over the general range of the year. So we can see that it picks up around 90 degrees solar longitude, which is equivalent to the summer solstice, and stays peaked throughout summer months and then quickly diminishes around 140 degrees solar longitude. And we can also see it's most active between 10 degrees south and 30 degrees north latitude. And because of these cloud masks, we can also analyze them monthly. And so here is half of Martian year 32 in addition to Martian year 33. And we can see that if I can take cloud masks and average them by month, which is roughly 30 cloud masks per month, we can see that there's activity earlier in the summer, which then diminishes quickly and then comes back again, which is consistent with other analyses done by previous papers and also with the last slide. These cloud maps can also be used in tandem with other climate models that can take interpretations of the Mars climate. We are going to specifically use the LMD's Mars Climate Database, which is based off their general circulation model. And I wanted to determine whether there's any correlation between these cloud masks and the MCD. We will be specifically looking at their water ice cloud column values. And in the lower right-hand corner, we can see a comparison throughout the year at various latitudes
2
of our
minutes.
cloud mask. Thank you. And we can see that it is most prevalent in 10 degrees south up to 30 degrees north, which is again consistent with our previous slides. And we also do see an interesting artifact at 30 degrees north, where it's not, we have this interesting spike, but this is likely a polarized cap interfering with their data. We can also look at this through a larger area, through latitude and longitude. We can also see that Hellas Peninsula and the Tharsis Mons are the locations where we have most clouds, and this is also looking at during peak activity. And this also shows us that we can detect optically thin clouds. As we can see, we're detecting much brighter clouds and also quite thin ones. So in summary, I designed a deep learning framework that identifies Martian clouds. It can replace the existing manual and semi-automatic techniques. It identifies clouds at almost 97% accuracy with high resolution and high speeds. My desktop computer can compute these masks in less than 3 seconds each. And the applications of these cloud masks we have shown in the past few slides, where we can do interesting interpretations. And potential future model improvements are to potentially include carbon dioxide ice and dust classification. I hope this tool will be of use to other scientists. Machine learning is a very interesting field, and I hope it can be integrated into more Martian exploration and planetary science. And I would like to thank my mentor, Dr. Scott Guzewich, for providing guidance and initial inspiration for this project. Thank you.